Hello everyone, I'm Ruxue, and I'm thrilled to present our paper titled From Denoising Trailing to Test Time Adaptation, Enhancing Domain Generalization for Medical Image Segmentation. Today I'll be sharing the key insights and advancements we made in the realm of medical image segmentation. Let's delve into the details and explore the exciting journey from denoising trailing to test time adaptation. Let's start by exploring the motivation behind our work. In the realm of medical image segmentation, we face two primary challenges: limited data and domain generalization, which refers to the model's performance on unseen domains. For medical images, they often display distributional discrepancies due to factors such as different equipment and so on. Such discrepancies challenge models to generalize to unseen domains. Most domain generalization methods involve extracting domain invariant features from multiple domains. However, this proves challenging in medical image segmentation due to the limited data. Facing two challenges in medical field, a more realistic yet challenging setting is single domain generalization, a scenario where only one single domain is available for trailing. The most single domain generalization methods focus on data augmentation or generalization. We propose to solve these challenges in a new way. We are motivated by the self-supervised learning, which is frequently employed to address the issue of limited data. In addition, integrating self-supervised learning into the framework presents a novel approach to tackle the single domain generalization challenge. Now, let's delve into the heart of our solution, self-supervised learning. So, how to integrate the self-supervised learning? We introduce a Y-shaped framework, one branch for the original segmentation and another branch for the self-supervised learning. In our context, Y-shape serves a dual role, using the potential of unlabeled data by the self-supervised branch and enhancing the model performance on unseen domains. Because Y-that introduces a critical feature known as test time adaptation, which aims to utilize the distribution information from the test data to quickly adapt models with a few gradient steps at test time. The second key problem is which self-supervised learning method. We observed that the medical images often suffer from various types of noise due to limitations in imaging technology or variations in imaging protocols, which is one of the key factors contributing to domain shift. So, integrating self-supervised denoising helps the model to extract features from clean images and supporting test time adaptation. Let's take a closer look at the details of our method. As illustrated in the overview figure, our approach, named DNet, is built upon the UNet architecture. In DNet, the encoder is followed by two decoders: the segmentation decoder for pixel-wise segmentation task, and the denoising decoder for self-supervised denoising. For the self-supervised denoising, we use the noise-to-void scheme. In noise-to-void, the assumption is that the noise is pixel-wise independent, and the information about noise is not carried in neighboring pixels. This allows for effective denoising by predicting pixel values replaced by their neighboring pixels. The noise-to-void network can be trained by minimizing the empirical risk. This process allows the network to denoise the image by learning from surrounding pixels. It may not capture or predict the pixel-independent noise. Let's elaborate on the training phase. To start our approach, we initiate the model by pre-training the segmentation decoder using a well-trained denoising network. The rationale behind this is to leverage the knowledge gained from the denoising task, exploiting the overlap between segmentation and denoising tasks. We aim to ease the complexity of the segmentation task and enable more effective joint trailing of the two tasks. During the joint trailing phase, we follow the noise-to-void scheme for both input processing and denoising loss calculation. For the segmentation task, we employ the standard dice loss. For the joint loss, the weighted function is employed to enable the denoising loss to gradually start working during the training process. At test time, our approach integrates two crucial adaptation strategies: target domain adaptation and noise-corrupted input adaptation. Considering that the single test volume can give us a hint about its distribution, we aim to optimize the model parameters with each unlabeled test volume. Once each test volume arrives, we optimize the self-supervised denoising loss while the segmentation decoder is frozen. And we only adapt the parameters in the bench normalization layers. For the noise-corrupted adaptation, indeed, it is apparent that the modified input whose pixels are replaced by neighboring pixels leads to the loss of information. To further preserve the information, we can get several inputs after being randomly masked. Then we can make predictions on all these masked inputs and merge the predictions. It is a novel test-time augmentation strategy designed for our method. All these are the key elements of our method. Next, we'll move on to the experiments to prove how well our approach works. We'll also discuss some limitations. We use the public chaos dataset for source domain trailing and in-domain testing. Additionally, for assessing out-of-domain generalization, we employed local datasets like LOMO and EU, along with the public LITS dataset. We compared our method against several domain generalization and test-time adaptation methods. In the final two rows, our results stand out, demonstrating superior performance, especially in assigned domains. Notably, on the largest and most diverse LITS dataset, our improvement is significant. The comparison also indicates a significant enhancement before and after the DTTA. In our visualization comparison, we provide a comprehensive view of the results. The visual assessment further underscores the efficiency of our method, showing notable improvements in segmentation quality and accuracy across various datasets and domains. Let's delve deeper into a closer analysis of the DTTA improvement. Overall, DTTA increases the average dice by 0.5% with a notable increase of 1.95% in the LITS dataset and 4.59% in the tumor dataset, a subset of the LITS dataset with more pronounced domain shifts. This observation reveals that for certain test data with large domain shifts and poor segmentation results, DTTA can extract information from the test data and adapt the model according to the test domain to significantly improve the segmentation results. This is also visually evident in the left figure. In the ablation study, we highlight two important experiments. The first experiment validates the effectiveness of weight, while the second compares our pre-trailing strategy with other approaches, providing evidence of its efficiency. If you have any questions or would like further details, Feel free to reach out. Thank you.